Hey all, we are continuing our work in chapter 12, and today I've just got two examples for you, so we'll see how long those take. But we're going to be looking at deflection for our beam in the context of distributed loads. So we're still thinking about what different supports are doing and how we're going to connect boundary equations to our displacement equation. We're also going to be thinking about creating those functions by applying that moment curvature relationship, that second derivative stuff that we're doing. So I want to talk about how to deal with both types of distributed loads that we've dealt with in these classes, both constant and linear, and show how that is going to affect our equation. So just as a review here, our steps for these problems, we're going to be taking a look at support reactions first before we slice, because those are going to help us get numbers in our equations. Then we're going to create the moment as a function. Our next step is going to be to integrate. This is where we have our new equations. So we have EI times our slope of our displacement. I guess that's probably better to call deflection. We're going to integrate our moment, and then EI times our displacement is going to be integrating our moment. So we're just going to integrate that again. We're going to integrate our integral of the moment. Then we're going to go ahead and step 4 and take a look at our boundary conditions and continuity. So we're going to be solving for those constants of integration. Continuity. We know what our boundary conditions are going to be based on the types of supports that we have. For example, if we have a support like a pin or a roller, our displacement is going to be equal to 0. So we can set the displacement function equal to 0 at that x value. If we have a fixed end, which I think we're going to be looking at today, yes, we will see one of those today, then we know both the slope and the displacement are 0. Yippee. So let's dive in. Let's take a look at fundamental problem 12.4. We have a beam here that's pinned at A and has a roller at B. It's 12 foot long, and there's a 100-pound per foot distributed load acting along the length of the beam. We want to figure out what the maximum deflection is going to be of this simply supported beam. It's made of wood and has a modulus of elasticity of 1.5 times 10 to the 3 KSI and a rectangular cross section with a width of 3 inches and a height of 6 inches. Good news is here, because we have no concentrated load acting anywhere, we only need one x value. We can just define x1, and that's it. No x2 needed for this problem because I don't have any places where that's going to dramatically change. Huzzah. Step 1, supports. I'm going to just write them out again. I'm going to give them to us. If you want to go through and solve them, you can. So feel free to pause and you can go through and solve for the supports. So that way you can see what it feels like to do the problem as a whole. I want to focus on our new content today. The good news is this one is fairly easy if you just want to rely on symmetry. We have 100-pound per foot times 12 feet. So that's going to be 1,200 total for our distributed load. That's symmetrically applied. So we have 600 pounds at both AY and BY. If I want to take a look at my moment then for step 2, moment function. I want to slice at some generic location x1. I still have a distributed load in there, but the maximum value, if I have x1 as my length of that section, and 100 as my height, because it's a distributed load, right, then the resultant force is going to be 100x1. I got my internal moment. I have my 600-pound support reaction. So if I want to do my net moment equals 0 about the slice, I have my moment as a function. I'm going to choose counterclockwise as positive as per usual. So we have plus 100 x1 times the distance that is going to act from my slice, which is going to be x1 over 2. Don't forget about that. And then that's going to be minus 600 x1. So my moment, and as a function of x1, is going to be 600 x1 minus 50 x1 squared. Checking my notes. Great. Everything's in pounds and feet, so this is going to end up being pound feet here. So now I just need to integrate. So we're going to get our slope, EI times our slope uh, of x1 as a function, right? We're going to integrate this once. So I'm going to have 300 x1 squared minus 50 over 3. We're going to leave that as it is, x1 cubed. I only like to divide the numbers in if they're nice looking. We're going to have C1. That's going to be pound feet squared. Otherwise, I end up with a bunch of like repeated decimal places. So fewer decimal places that I can work with, the better. That's me personally, though. If it helps you to just have one number, go for it. We're going to integrate again to get our displacement as a function of x1. So that's going to be 100 x1 cubed. Then we're going to have minus 50 over 12, x1 to the fourth, plus C1 x1 plus C2. And the units on that are going to be pound feet cubed. So you can see how having that distributed load is going to introduce this extra force, where if we didn't have that, it would just be the x cubed function. But now because we have that distribution, we have an x to the fourth term in our equation. So that's what a constant distributed load is going to introduce by the time that we're looking at this. Looking at our boundary conditions. Oh, good. I do have 2 slides for this if we need it. So let's not cram stuff in anywhere. Step 4 is going to be our boundary, our continuity conditions, but we actually don't need continuity here. Boundary is going to be enough because I only have 2 unknowns. So what do we know boundary condition wise? Well, our displacement at x1 equals 0 is going to have to be equal to 0, which is going to just reduce all of that down to C2. We basically got 100 times 0 cubed minus 50 over 12 times 0 to the fourth plus C1 times 0 plus C2. So C2 is going to be equal to 0. Don't have to worry about it. We can take that out of our equation. We also have the fact that there's a roller at B, so we can take a look at x1 equals 12 is also going to have to be 0. This is going to be 100 times 12 cubed minus 50 over 12 times 0 to the fourth. Not 0. I'm sorry. I'm just copying the above thing. 12 to the fourth plus C1 times 12 is going to give me a C1 when I solve that of negative 7,200. And then it's going to be pound feet squared based on the units where we introduced C1. This allows me to generate the equations that I need. We're looking for maximum deflection. So let's take our equations I'm going to the next slide here. Do I want to copy those over or just rewrite them? We'll copy. So the same problem, right? But we're looking for the maximum displacement. Where is our displacement going to be maximum? Some of you might have been able to analyze that by symmetry if we're thinking about our elastic curve here in this situation, right? Others of you might have come up with the calculus explanation, which is going to be where the slope is zero. Where our slope is zero, then our displacement's max. Others of you might have just sat there silently and waited for me to explain it. We want to find max displacement here. That's going to be our step 5, max displacement. So two different ways that we can look at it. It's maximum when the derivative of our displacement, which is theta, is equal to 0. So I could set my theta equation equal to 0 and solve for that x value. I don't really want to do that. What we're going to end up doing instead is just kind of analyzing this by symmetry. So this is going to be 6 feet by symmetry. Specify that's at 6 feet by symmetry. Okay, so I just want to plug in 6 because my displacement equation. So EI displacement at x1 equals 6 is going to be equal to 100 times 6 cubed minus 50 over 12 times 6 to the 4th plus C1, which is negative 7,200 times 6. This is going to come out to be negative 27,000. And because I know what the units are for EI times displacement, that's going to be pound feet cubed. That's the reason we want to keep track of that stuff. Now, I just want the displacement at x1 equals 6. So I'm going to divide the EI stuff over. So in my numerator, I've got negative 27,000 pound feet cubed. In my denominator, I have 1.5 times 10 to the 3 KSI, and the inertia, which is going to be 1/12 base times height. So 1/2 times 3 inches times 6 inches cubed. So I can see in this situation that I have a whole mix match of units. And if I wasn't keeping track of units with the pound feet cubed, then I would just be plugging these numbers in and then just guessing at what things were going to be at the end. I need to be able to convert stuff. I think the easiest thing to do, well, there's multiple ways you can do that. We can either convert feet to inches, inches to feet. I'm going to go feet to inches here. So we have 12 inches per foot. And I'm going to just cube that. So 12 cubed will get rid of those feet cubed and give me inches cubed up top. I also have the kip in the KSI. So what we can do here is just divide by an extra 1,000. So we have 1 kip is going to be 1,000 pounds. And I would have done that probably when I rewrote this out up top. I would have just done negative 27 kip feet squared, but we can cancel out the pounds that way too. This allows us to then just calculate some numbers to get negative 0.576 inches. So kips will cancel. I have inches squared and inches to the 4th in the denominator, which will leave me inches squared in the denominator. and I have inches cubed up top. So I'm just left with inches. Very similar to the last problem, just with this extra distributed load. So we have an extra term in our function. Okay. Second example for today, problem 1222. We want the elastic curve for this cantilevered W14 times by 30 beam. What the heck does that mean? Well, I will show you. This is something kind of setting us up for what we are going to look at in chapter 13, because there's some extra stuff in chapter 13 where they actually define I-beams based on the dimensions. So you can just go grab inertia from a table. We will. I need to find the table, but that's my problem right now, not yours. We want to specify the maximum slope and the maximum deflection for this beam. So we have the modulus of elasticity is 29 times 10 to the 3 KSI. We see that the beam is fixed on the left at A. There's a linear distributed load that starts at 0 at that point to a maximum of 3 kip per feet at B at the right end of this 9-foot long beam. So we're going to do the same process. We just have to deal with this linear distributed load, which is going to be a little bit different. I'm going to worry about the W14 by 30 until I have to worry about it. Let's just keep going through this the way we normally would right now. Step 1, supports. We need supports? Not really. We could start at B if we wanted to, but it's easier to slice where they already give us x equals 0. So sure, right? Let's get them. It doesn't hurt to have them in these situations. So I think we should just, in chapter 12, get used to just grabbing units for the sake of having them. Or by units, I mean support reactions. So if I'm looking at this distributed load here, I know it's going to reach a maximum at 6 feet. And that's going to be my FR. And then I'm going to have, I know AX is going to be 0, so we're just going to be looking at AY and a moment, which is going to be acting the other direction. But that's fine. I will just get MA as negative 81 kip feet, and I'll get AY as 13.5 kip. So I can take those into my step 2, which is going to be the moment as a function. So we're going to slice at this location x1. I'm going to redraw my support moment. So it is going to be positive. So that'll be 81 kip feet counterclockwise. AY is going to be that 13.5 directed up. The length of this section is going to be x1. And then I have a distributed load, which is going to be some resultant force, 1/2 times W times x1. Right? I need to figure out what W is. I need a function for my distributed load. So what we're going to do here, then if I want this W at my generic x1, I'm going to use the same kind of ratio logic that we looked at before. W at x1 is going to be the same as 3 at 9, which gives me the fact that W is going to be 1/3 x1. So my resultant force here is going to be 1/2 times 1/3 x1 times x1, which is going to give me, or we can just wait and plug it in later. What did I do? Yeah, no, it's going to be 1/6 x1 squared, right? So that's my resultant force. And that's going to be acting at how far away from our cross section? That's going to be x over 3 away. Why did I label it like that? We'll never know. Right, so that distance is going to be x over 3. Yikes, right? Okay, linear distributed loads, so not as fun. But if I'm going to do my net moment equals 0, with counterclockwise is positive, I'm going to end up with m plus 81 minus 13.5 x1, and then plus my 1/6 x1 squared times x1 over 3. So this is my FR times that distance. At the end there. My moment's already a moment, so I'm not multiplying it by anything. So those are the two new things that we're looking at here. Dealing with fixed supports, it's already a moment, it just gets added in. Dealing with a linear distributed load, we've got that x squared term in our resultant force because our W is a function of x and our width is also an x. So it becomes more complicated. But as long as you're doing everything in terms of a generic distance x, you are in good shape. So my internal moment here is a function of x1. Once again, we only have one dimension that we need to worry about here because there's no place where our forces are going to dramatically change. So our moment as a function of x1 is going to be 13.5 x1. I just like to start with the positive stuff first. Minus, minus 81 minus 1/18 x1 cubed. Is that correct? Checking my notes. Sure. And the units for that, we've got kip feet. Everything was in kip and feet when we were multiplying them together. Step 2 is going to be to integrate. So we have EI theta as a function of x1 is going to be the integral of that, which is going to be 13.5 over 2 x1 squared minus 81 times x1 minus, oh geez, 4 times 18 is going to be 1 over 72, x1 to the fourth. We added an extra dimension of distance in there, so that's going to be kip feet squared now for my units. Oh, plus C1, plus C1, plus C1. Got it. We're going to do one more integration for our displacement. The integration is the easy part here. So that's going to be 13.5 over 6 x1 cubed minus, I don't even want to do half of 81, 81 over 2 x1 squared minus 72 times 5 is going to be 1 over 360 times x1 to the fifth plus c1 x1 plus c2. And the units for that will be kip feet cubed. Internal loading stuff, you know how to do that. We've done a bunch of those types of things for our moments. We're just thinking about the distance in terms of being x. This integration stuff, also something you can totally do. Calculus was so long ago for you. You're a master at power rule. Like, you're going to be fine. You can do this. In fact, in our next video, I'll pause for you to get a sense to do integration here. I am now on step 4 because step 3 was integrate. It's going to be our boundary conditions / continuity. So what do I know here? What are my boundary conditions? I have a fixed supported A, so what does that mean? That means for us that our displacement at x1 equals 0 is 0, which means that C2 is going to be 0. So I can ignore that. Our other boundary condition for a fixed support, which is the first time we're dealing with it, is that our slope at x1 equals 0 also is going to have to be 0 because it's fixed support. We just want our beam to be kind of coming out of the wall perpendicularly, right? And then it's going to bend it down. So if theta is equal to 0 when I plug in 0, that means that C1 is also equal to 0. And so I get to not think about any of those constants of integration. Hooray! So that means I can just take those to find maximum slope and maximum deflection or displacement, right? I want to find both of those maximums. All right, we're going to jump to the next page here. Step 5 is going to be for our max displacement and our max theta. Now, if we're taking a look at this beam, knowing that it needs to have no slope right away, and then we're pushing down more and more as we're getting to the end, where are our maximum slope and maximum displacement going to be at B, right? By inspection, uh, both maximums are going to be at B. So we can get our maximum slope first. We're going to plug in 9 for our theta equation. This is going to be 13.5 over 2 times 9 minus 81 times 9 minus 1 over 72 times 9 to the fourth, which is going to come out to be 273.375. And oh no, what are my units for that? I have a bunch of weird numbers. Well, we kept track of those. It's going to be kip feet squared. So if I want to look at the theta at 9, that's going to be 273.375 kip feet squared over 29 times 10 to the 3 KSI. And I'm going to need the inertia now. So let's talk about how to get that. When you have a beam that's described as this W14 by 30, we actually have a whole appendix at the back of the book. Now this is my problem. We have a whole appendix at the back of the book. It's actually Appendix B. And you're going to see this more in the next section here. So in Appendix B, it has a whole bunch of tables based on different structural shapes. So we have geometric properties of these structural shapes. You can see that they've got different designations for beams in terms of like inches by pound feet here. And then it gives you the dimensions of all of those beams, area, depth, the thickness of the web, the base, like width and thickness. It also gives you the inertia about different axes. I think I picked one where we can actually kind of look at this picture and it's got these labels here nicely for us. Um, so we want, what was it? What was it? 14 by 30 here. Those are 12s. Nope. Is it on the previous page? It's a good question. Yes, it is. And I have it highlighted, right? So I want 14 by 30. There's two inertias that they're giving us. We want this inertia about the horizontal axis. So that's going to be the x-x axis, which we can verify from this image here, right? We're applying the distributed load. So our bending is going to be about our horizontal axis as per usual. So we're going to grab the inertia off of this x-x column for our 14 by 30 beam. That's going to be 291 inches to the fourth. And that's it, right? We can just look it up on a table. We don't have to calculate inertia. Wouldn't of our lives in chapter 6 been so much easier if we knew about that? Well, we know about it now. We needed to know how to calculate it so we could get it if it wasn't on the table. It's going to be 291 inches to the fourth. Once again, I need to convert my feet to inches here. So we're going to do 12 inches per foot. And it's just going to be squared because we're looking at our slope. This is going to give us negative 0.00466 radians. And we're going to do the same thing for our displacement. Our displacement at 9, I guess I didn't write that one out for you, but I will now. I didn't do it for me, I guess, then. I'm doing it for you. I didn't do it for me. If we're plugging in the 9 there, then we're going to have 13.5 over 6 times 9 cubed minus 81 over 2 times 9 squared minus 1 over 360 times 9 to the fifth, which is going to come out to be negative 1804.274. That's going to be kip feet cubed. And we're going to divide all of that by our EI from the above. So our displacement at 9 is going to be that negative 1804.274 kip feet cubed times 12 inches per foot cubed, 29 times 10 to the 3 KSI, 291 inches to the fourth in our denominator, which is going to give us negative 0.369 inches. Plugging in the numbers is the easy part. Integrating's okay. I think the boundary conditions are one of the tougher pieces, but I think the hardest part is going to be getting your internal loadings. Being able to keep track of what's going on with your distributed loads, slicing it at a generic location X, remembering to multiply the things that you need to multiply. So getting your initial moment part is going to be the part where you're probably going to want to focus most of your time, and then just kind of go through and integrate for your displacements. Hopefully this gives you a picture of how to deal with our fixed supports at the end. We saw that that just gave us an extra moment in our equation that we needed to account for. So we just had a random 81 in there, not times anything. And then we also looked at how to deal with linear distributed loads in this problem, remembering that we have that 1/3 distance from the highest point, how to find our distributed load as a function. So that way when we get our resultant force is 1/2 times that function times x1, we can see where that x1 squared is coming from. That's going to be it for our kind of generic displacement and slope kind of problems. In the next video, we're going to look at how we can use this process to be able to solve for unknown support reactions when equilibrium is not enough. So I will see you there in that video. Keep up the great work. We're almost done.